Hello everyone, in this video we are going to go over Newton's first law and do a few examples. So Newton's first law says if an object is in a state of rest or in a state of constant velocity motion, then the net force acting on the object must be zero. You can also say it the other way around. If the net force acting on the object is zero, it must be either at rest or doing constant velocity motion. So that's why we have the equivalent sign here. And the net force, of course, means the vector sum of all the forces acting on the object. So if you want to put Newton's first law into equation, you have net force equals 0, give us acceleration 0, and acceleration 0, then it will be either at rest or doing constant velocity motion. The velocity doesn't change. Now keep in mind that because force is a vector, so if force is a vector, so force equals 0 should give us in 2 dimensions your net force in x direction is 0 and your net force in y direction is 0. So in 2 dimensions we should have 2 equations from Newton's first law. So that's how are we going to solve the problem. First you need to select the object that is in equilibrium. Then you need to draw a free body diagram. You need to know how to draw a free body diagram for the object. Now you only draw a free body diagram for the forces acting on the object. Then you need to set up your coordinate system, your x and y axis, and then you find all the components of the force in the x direction, all the components of force in the y direction, and then you have 2 equations. You have net force in x direction equals 0, net force in y direction equals 0. Then you solve for any unknown quantity from those 2 equations. So let's see a very simple example. So you put a block which is 5 kg on a table. So what would be the normal force between the block and the table? So you draw a free body diagram on the block. So it's already drawn on the right. So we can do it again. You have a block. It has weight pointing down. It has normal force pointing up. Now of course the block is not moving, so the net force is 0. You build your coordinate system, that's your x, that's your y. So you can see in the x direction there is no force, so we're not concerned with x direction. In the y direction we have normal force pointing in the positive y, so it's positive weight pointing in the negative y. So negative is 0, so give us normal force equals weight equals 5 times 9.8 newtons, so it should be 49 newton. Yeah, so the normal force is 49 newton in this part. Now let's say a little bit more complicated. Now you still put the block on the table. You apply a force to the right, and the force applied is 10 newton. And the block is not moving either, so there got to be some other force in this direction, which should be our static friction if the block is not moving. So you see, if you draw the free body diagram for the block, you have normal force, weight, force applied, friction. So in the y direction, nothing changed. In the x direction is force applied. Subtract static friction should give us 0. The y direction normal force subtract weight should give us 0. So and it asking for friction. So we solve for equation in the x direction. Friction should equals to the force applied, which is 10 Newton. Now, a little bit more complicated problem. You have a ring. We use the ring to move an engine, and you have two tension acting on the ring, T1, T2, and the direction are as shown. So this angle is 10 degrees, this is 80 degrees. What we know is the weight is 3150 Newton. Given by the problem, we want to know what is tension T1 and T2. So always, first of all, we need to draw the free body diagram on the ring. Now, of course, this is an equilibrium problem that says the ring is doing constant velocity motion. So we have the ring we're interested in. You have T1, T2, W. You have your coordinate X and Y. So let's find out the components of each of the force. So we have T1, T2, and W, X component, Y component. See the X component of T1. X component should be this one. So it's pointing to the negative direction, negative magnitude of T1. And then you should use sine 10 degree because it's opposite side of this angle, 10 degree. And then similarly y, which should be magnitude of T1, cosine 10 degree because y component is this one for T1. And this is your T1. So this should be your x component of T1, T1x, and this is your y component of T1. And you do the same thing. You have x component of T2, T2 sine 80 degree, y component of T2 cosine 80 degree, x component of weight 0 of course because it's pointing in the y direction, y component negative y. So you sum all these three, you have net force in x, you sum all these three, you have net force in y. And you have net force in x equals 0, net force in y equals 0, so you have two equations. Net force in x direction. Oh, sorry, this is T2. Oh, yeah, T1. What I'm doing. T1 so you can solve for T1 from equation 1. Equation 1 should give us T1 in terms of T2. And then you let's call this one 3. So you plug 3 into equation 2. So you can replace T1. So replace T1 by this term. So let's create a 4. So in equation 4, you only have one variable that you don't know, which is T2. So you can solve for T2. And in the end, you find that T2 is 582 Newton. And now you put T2 back into equation 3. You can solve T1, 3,300 Newton. So you solved this problem. You see, for this kind of problem, what you always need to do is follow the procedure. First, draw the free body diagram for the object you are interested in. For all the forces, find the x component, find the y component, then you build the equation. Net force in the x direction is 0, net force in the y direction is 0. And then you solve these two equations for any variable that you don't know. Hope that's helpful for you understand Newton's first law.